This is another video in my series on alternating current. In this video, I'm going to take a look at harmonic motion. You will find this topic along with my other courses entitled Power Analysis in AC Circuits. You can access this and my other courses on my Stan Store at this web address. Let's consider an inductor capacitor in parallel. This circuit is known as an electrical pendulum. In order to see how it works and why it is called a pendulum, I'm going to apply a DC source to this parallel circuit. What happens immediately is the capacitor will charge to the source voltage and the current will increase until Ohm's law tells us that it will reach a value of the source voltage divided by the resistance of the circuit, which will flow through the inductor continuously as long as the switch is closed. Once the switch is opened, this will, when the electrical pendulum will start to operate. The current from the source immediately stops and the current through the inductor will then be zero. The capacitor, then being at the source voltage, will start to discharge through the inductor. The voltage continues to drop until the current will continue to rise. At some point, the capacitor will start to charge in the opposite direction due to the current flowing. It will then reach a negative maximum, at which point the current will then be zero and the capacitor will then discharge in the opposite direction. These oscillations continue in a sinusoidal fashion but will be out of step by 90 degrees to each other. This is similar to the motion of a mechanical pendulum that at the bottom of its swing has zero potential energy but is at a maximum of kinetic energy. As it swings to the right, it starts to slow down, losing its kinetic energy, but as it rises, it builds its potential energy until it reaches a maximum height, at which time it reverses motion and starts in the other direction. This oscillation between kinetic and potential energy over time maps out sinusoidal waveforms, which, like the electric pendulum, are 90 degrees out of phase to each other. This is what is known as harmonic motion. The same is true for the capacitor inductor circuit. The rate of oscillation is strictly dependent on the size of the capacitor and inductor, not on the amount of the voltage or the current at each respective peak in the waves. The ability for such a circuit to store energy in the form of oscillating voltage and current has earned it the name a tank circuit. Its property of maintaining a single natural frequency regardless of how much or how little energy is actually being stored in it gives it a special significance in electric circuit design. However, this tendency to oscillate or resonate at a particular frequency is not limited to circuits exclusively designed for that purpose. In fact, nearly any AC circuit with a combination of capacitance and inductance, commonly called an LC circuit, will tend to manifest unusual effects when the AC power source frequency approaches that natural frequency. This is true regardless of the circuit's intended purpose. If a power supply frequency for a circuit exactly matches the natural frequency of the circuits of the LC combination, the circuit is said to be in a state of resonance. The unusual effects will reach maximum in this condition for resonance. For this reason, we need to be able to predict what the resonant frequency will be for various combinations of L and C and be aware of what the effects of resonance are. This is all that we have time for in this video. However, stay tuned because in my next video, I will show you how to calculate the resonant frequency of an LC circuit. Before concluding this video, I want to make you aware of Anchor's Flash Weekend Sale that is ending after tomorrow. These are just a few of the items that are on sale, and to look at the full extent of the sale, simply go to this web address. As a reminder, all of the letters in this web address are lowercase, with the exception of the second last letter, which is an uppercase G. This video is part of my electrical technical information series. Be sure and stay tuned, as I will also from time to time be reviewing electrical products that in my opinion are worthy of paying attention to. This address will give you access to the supplier of aforementioned products, and it is also the connection to obtain a free copy of my 50-page electrical power crib sheets.